Master of Architecture. Mh4221 Geographical Information Systems, GIS, for built environment. Subject, concept outline and short notes. Objectives. Geographical Information Systems for built environment. Geographical Information Systems, GIS, can be a valuable tool for managing and analyzing data related to the built environment. GIS technology can provide a way to integrate and analyze various data sources, such as building footprints, land use patterns, transportation networks, demographic data, and environmental factors. Here are some examples of how GIS can be used for the built environment. Planning and development. GIS can be used to analyze land use patterns, assess site suitability for development, and create development plans. It can also be used to visualize and communicate proposed developments to stakeholders. Infrastructure management. GIS can be used to manage and analyze infrastructure data, such as water supply, sewerage systems, and transportation networks. This can help improve the efficiency and effectiveness of maintenance and repair programs. Environmental management. GIS can be used to analyze and manage environmental data related to the built environment, such as air quality, water quality, and noise pollution. This can help identify areas that require remediation and inform decisions about future development. Emergency management. GIS can be used to support emergency management by providing real-time information on the location and status of critical infrastructure, such as hospitals, evacuation routes, and emergency shelters. Overall, GIS technology can provide valuable insights and inform decision-making related to the built environment. By integrating data from various sources, GIS can help identify patterns, trends, and relationships that may not be apparent through traditional methods of data analysis. Introduce role of GIS in architecture and planning. GIS technology plays an important role in architecture and planning by providing a powerful tool for managing and analyzing spatial data related to built environments. Here are some key ways that GIS can be used in architecture and planning. Site analysis. GIS can be used to analyze the physical and environmental characteristics of a site, such as topography, land use, soil type, and natural hazards. This information can help architects and planners identify potential design constraints and opportunities. Urban design and planning. GIS can be used to create and analyze different scenarios for urban development, such as zoning regulations, land use planning, and transportation networks. This can help architects and planners to make informed decisions about the design and layout of urban environments. Infrastructure planning and management. GIS can be used to manage and analyze data related to infrastructure systems, such as water supply, sewerage systems, and transportation networks. This can help architects and planners to optimize the location and design of infrastructure systems. Environmental analysis. GIS can be used to analyze and manage data related to environmental factors, such as air quality, water quality, and noise pollution. This can help architects and planners to design environments that are both functional and sustainable. Stakeholder engagement. GIS can be used to create interactive maps and visualizations that can be shared with stakeholders. This can help architects and planners to communicate design proposals and engage with the public. Overall, GIS technology can provide architects and planners with a powerful tool for analyzing and managing spatial data related to the built environment. By integrating data from various sources, GIS can help architects and planners to make informed decisions about the design and development of urban environments. Give basic familiarity with the concepts, tools, and techniques of GIS. Geographic Information Systems, GIS, are computer-based systems designed to capture, store, manipulate, analyze, and present geographically referenced data. GIS can be used to visualize, query, and interpret spatial data in order to support decision-making in a wide range of applications. Here are some basic concepts, tools, and techniques of GIS. Geographic data. GIS data is organized into layers that represent different types of geographic features, such as roads, buildings, and land use patterns. These layers are stored in a database and can be analyzed and visualized in combination with other layers. Coordinate systems. GIS data is typically referenced to a coordinate system, which is a mathematical system that defines the location of geographic features on the Earth's surface. Common coordinate systems include latitude and longitude and the Universal Transverse Mercator (UTM) system. Data capture. GIS data can be captured from a variety of sources, such as satellite imagery, aerial photography, GPS devices, and field surveys. Data can be entered into a GIS database using a range of techniques, including digitization, scanning, and GPS. Data management. GIS data needs to be managed in order to ensure that it is accurate, complete, and up-to-date. Data management techniques include data quality control, data conversion, and metadata creation. Data analysis. GIS provides a range of tools for analyzing geographic data, such as overlay analysis, proximity analysis, and spatial statistics. These tools can be used to identify patterns, trends, and relationships in the data. Data visualization. GIS provides a range of tools for visualizing geographic data, such as maps, charts, and graphs. These tools can be used to communicate complex data in a clear and understandable way. Overall, GIS provides a range of powerful tools and techniques for working with geographic data. By combining data from multiple sources and analyzing it using GIS tools, users can gain insights into complex spatial relationships that may not be apparent through traditional methods of data analysis. How to get trained in the application of GIS for built environment. There are many ways to get trained in the application of GIS for built environment. Here are some possible options. Online courses. There are many online courses available that cover GIS and its application in the built environment. Some examples of online courses are offered by Udemy, Coursera, and ESRI Training. University courses. Many universities offer GIS courses as part of their degree programs in urban planning, architecture, and engineering. Consider looking into the GIS courses offered by universities in your area. Conferences and workshops. GIS conferences and workshops provide an opportunity to learn about the latest trends and technologies in GIS. Attendees can learn about GIS applications, case studies, and best practices, as well as network with other professionals in the field. Professional organizations. There are many professional organizations related to GIS, such as the Urban and Regional Information Systems Association, URISA, and the American Society of Photogrammetry and Remote Sensing, ASPRS. These organizations offer training, conferences, and networking opportunities. Self-study. There are many GIS resources available online, including books, tutorials, and documentation. Consider exploring the documentation provided by GIS software vendors, such as ESRI or QGIS, to learn more about GIS and its application in the built environment. Regardless of the training method you choose, it's important to practice GIS skills in order to build proficiency. Consider working on GIS projects related to the built environment, such as mapping land use patterns or analyzing transportation networks. This will help you gain hands-on experience and build your skills. Unit 1. Introduction to G.I.S. Geographic Information Systems, GIS, are computer-based systems designed to capture, store, manipulate, analyze, and present geographically referenced data. GIS integrates hardware, software, data, and people to support spatial analysis and decision-making. GIS allows users to view, query, and interpret data in a geographic context, providing a powerful tool for analyzing complex spatial relationships that may not be apparent through traditional methods of data analysis. By combining data from multiple sources, GIS can provide insights into the spatial relationships between different features, such as land use patterns, infrastructure systems, and natural resources. GIS data is typically organized into layers that represent different types of geographic features, such as roads, buildings, and land use patterns. These layers are stored in a database and can be analyzed and visualized in combination with other layers. GIS is used in a wide range of applications, including urban planning, natural resource management, emergency response, and business location analysis. GIS is also used in scientific research, such as analyzing environmental patterns or mapping disease outbreaks. Some common GIS software packages include ESRI ArcGIS, QGIS, and GrassGIS. These software packages provide a range of tools for data capture, data management, data analysis, and data visualization. Overall, GIS is a powerful tool for managing and analyzing geographic data. By integrating data from multiple sources and analyzing it using GIS tools, users can gain insights into complex spatial relationships that may not be apparent through traditional methods of data analysis. Defining the objectives of GIS in problems related to the macro environment. GIS can be used to achieve a wide range of objectives in problems related to the macro environment, such as natural resource management, disaster response, and regional planning. Here are some examples of objectives that GIS can help achieve. Mapping and analysis of natural resources. GIS can be used to map and analyze natural resources such as water, land, and forests. This information can be used to identify areas that are at risk of depletion or overuse, and to develop plans for sustainable resource management. Environmental impact assessment. GIS can be used to assess the environmental impact of proposed development projects, such as highways or industrial facilities. This information can be used to identify potential environmental risks and to develop strategies to mitigate those risks. Disaster response and management. GIS can be used to identify areas that are at risk of natural disasters, such as floods or earthquakes. This information can be used to develop emergency response plans and to coordinate disaster response efforts. Regional planning and development. GIS can be used to support regional planning and development initiatives, such as transportation planning, urban design, and economic development. This information can be used to identify areas of opportunity and to develop strategies for growth and development. Climate change analysis and adaptation, GIS, can be used to map and analyze the impacts of climate change, such as rising sea levels and changing weather patterns. This information can be used to develop adaptation strategies to help communities and ecosystems cope with the effects of climate change. Overall, GIS can be a powerful tool for achieving a range of objectives related to the macro environment. By integrating data from multiple sources and analyzing it using GIS tools, users can gain insights into complex spatial relationships and develop strategies to address environmental challenges. Outline of commercial and open-source GIS software and introduction to basic components of GIS software. Commercial and open-source GIS software packages are available for users with different needs and budgets. Some popular commercial GIS software packages include Esri ArcGIS, Trimble Geospatial, and Bentley Map. Open-source GIS software packages include QGIS, GrassGIS, and Saga GIS. Here is an outline of the basic components of GIS software. Data management. GIS software allows users to manage geographic data, including storing, retrieving, and updating data. This component of GIS software includes tools for importing, exporting, and converting data formats, as well as tools for data validation and error checking. Data analysis. GIS software includes tools for performing spatial analysis, which involves analyzing geographic data to identify patterns, trends, and relationships. This component of GIS software includes tools for calculating distances, areas, and volumes, as well as tools for generating maps and other visualizations. Data visualization. GIS software includes tools for visualizing geographic data, such as maps, graphs, and charts. This component of GIS software includes tools for generating high-quality maps with custom colors, symbols, and labels, as well as tools for creating interactive maps for web and mobile applications. Data sharing. GIS software allows users to share geographic data with others, such as through web services or file transfers. This component of GIS software includes tools for creating and sharing maps, as well as tools for managing data permissions and access controls. Data collection. GIS software includes tools for collecting geographic data, such as through field surveys, aerial photography, or satellite imagery. This component of GIS software includes tools for digitizing and georeferencing data, as well as tools for GPS data collection and processing. Overall, GIS software provides a powerful tool for managing, analyzing, and visualizing geographic data. The components of GIS software work together to provide a comprehensive solution for users with a variety of needs, from data collection to data analysis and sharing. Outline of spatial and non-spatial data. In GIS, data can be broadly classified into two categories: spatial and non-spatial data. Spatial data. Spatial data refers to data that has a geographic location or reference. This type of data is typically represented by points, lines, polygons, and other geometric shapes. Spatial data can include information such as the location of roads, rivers, buildings, and other physical features. Spatial data can also include attributes, which are characteristics or properties associated with a specific location or feature. Examples of spatial data include satellite imagery, aerial photography, topographic maps, and GPS data. Non-spatial data. Non-spatial data, also known as attribute data, refers to data that does not have a geographic location or reference. This type of data can include information such as population demographics, land use codes, and economic data. Non-spatial data can be used in conjunction with spatial data to provide additional context and analysis. For example, non-spatial data such as census data can be used to analyze population density and demographics in conjunction with spatial data such as satellite imagery and land use maps. It's important to note that while spatial data is typically represented as geometric shapes, these shapes can also include non-spatial data attributes. For example, a polygon representing a city boundary might include non-spatial data attributes such as population size and demographics. Additionally, non-spatial data can be geocoded to add a geographic reference and convert it into spatial data. For example, an address or zip code can be geocoded to assign it a geographic location and add it to a map. Overall, both spatial and non-spatial data are important components of GIS analysis. By combining and analyzing these data types, GIS users can gain insights into complex spatial relationships and make informed decisions related to a wide range of applications, from urban planning to natural resource management. Understanding of projection and coordinate systems. Projections and coordinate systems are critical concepts in GIS as they help to accurately represent and analyze spatial data on a map. Here is an overview of these concepts. Coordinate systems. A coordinate system is a reference framework used to represent locations on the Earth's surface. It is a set of mathematical rules that define how points, lines, and areas are measured and located on the Earth. Coordinate systems consist of a network of lines of longitude and latitude that intersect to form a grid. The most commonly used coordinate systems in GIS are Geographic Coordinate Systems, GCS, and Projected Coordinate Systems, PCS. Geographic Coordinate System, GCS is based on a spherical or ellipsoidal model of the Earth's surface. GCS uses a three-dimensional coordinate system to specify locations on the Earth's surface. GCS is measured in degrees of longitude and latitude and is expressed in decimal degrees. Projected Coordinate System, PCS is a two-dimensional representation of the Earth's surface that is flattened into a plane. PCS uses a grid system to specify locations on the Earth's surface. PCS is measured in meters, feet, or other linear units. Projections. A projection is a method used to transform a three-dimensional object, the Earth's surface, onto a two-dimensional plane, a map. Because the Earth is a three-dimensional object, it is impossible to represent its entire surface on a flat plane without distorting it. There are many different types of map projections, each with its own advantages and disadvantages. Some of the most common map projections used in GIS are Mercator projection. The Mercator projection is a cylindrical projection that preserves direction and shapes but distorts areas, particularly at high latitudes. Robinson projection. The Robinson projection is a compromise projection that attempts to balance the distortion of area, shape, and direction. Albers projection. The Albers projection is a conic projection that is commonly used for mapping large areas of the United States. It minimizes distortion in shape and area, but distorts distance. Overall, coordinate systems and projections are essential to accurately represent spatial data on a map. It is important to choose an appropriate projection and coordinate system for the task at hand to ensure accurate analysis and interpretation of spatial data. Preparation of map with appropriate format for specific purposes. Preparing a map with an appropriate format for a specific purpose is an important task in GIS. Here are some general steps that can be followed to create a map with an appropriate format. Determine the purpose of the map. Before creating a map, it is important to determine the purpose of the map. This will help to identify the appropriate data layers, scale, and projection to use for the map. Choose an appropriate projection and coordinate system. As mentioned earlier, choosing an appropriate projection and coordinate system is critical in GIS. The projection and coordinate system used for the map should be chosen based on the purpose of the map and the area of interest. Select the appropriate data layers. The data layers used for the map should be selected based on the purpose of the map. For example, if the map is being created for urban planning purposes, data layers showing roads, buildings, and land use may be included. Customize the map layout. The layout of the map should be customized to meet the specific needs of the project. This includes choosing an appropriate scale, adding a legend, scale bar, and north arrow, and choosing an appropriate color scheme. Export the map. Once the map has been created, it should be exported in an appropriate format for the intended use. Common formats for exporting GIS maps include PDF, JPEG, and PNG. Overall, creating a map with an appropriate format requires careful consideration of the purpose of the map, the data layers used, and the layout of the map. By following these general steps, GIS users can create maps that are effective in communicating spatial information for specific purposes. Unit 2. Spatial and Attribute Data Input. Spatial and attribute data input are critical steps in GIS data management. Here is an overview of these concepts. Spatial data input. Spatial data input involves the collection and acquisition of spatial data. This can be done using a variety of methods, including field surveys, remote sensing, and GPS data collection. The data collected during this process may include point data, line data, or polygon data. Point data. Point data represents a specific location on the Earth's surface, such as the location of a tree or a water well. Line data. Line data represents a linear feature, such as a road or a river. Polygon data. Polygon data represents an area or a boundary, such as a city or a county. Once the data has been collected, it can be input into a GIS using a variety of methods, including manual digitization and automated feature extraction. Attribute data input. Attribute data input involves the collection and acquisition of non-spatial data that is associated with spatial data. This can include data such as demographic data, land use data, and environmental data. Attribute data is typically stored in a tabular format, with each row representing a specific geographic feature and each column representing a specific attribute. During the attribute data input process, data is typically collected using surveys, questionnaires, or other data collection methods. The data is then entered into a database or spreadsheet, where it can be linked to the appropriate spatial data. Overall, spatial and attribute data input are critical steps in GIS data management. By accurately collecting and inputting data, GIS users can ensure that their analyses and interpretations of spatial data are accurate and reliable. Passive and active remote sensing, image processing, spectral signature curve, GPS, aerial photograph, satellite imagery, LiDAR, and drones. Remote sensing refers to the process of acquiring information about the Earth's surface without physically being in contact with it. Remote sensing technology uses a variety of sensors to collect data about the Earth's surface, which can be used in GIS analysis. Here is an overview of some of the key remote sensing technologies and techniques. Passive remote sensing. Passive remote sensing involves the measurement of natural energy emitted or reflected from the Earth's surface. This includes techniques such as aerial photography and satellite imagery. Passive remote sensing is useful for mapping and monitoring land use and land cover, as well as for monitoring changes in vegetation and water resources. Active remote sensing. Active remote sensing involves the transmission of energy from a sensor and the measurement of the energy that is reflected or scattered back to the sensor. This includes techniques such as LiDAR, light detection and ranging, and radar, radio detection and ranging. Active remote sensing is useful for measuring topography, vegetation structure, and soil moisture. Image processing, spectral signature curve. Image processing refers to the process of analyzing and enhancing remote sensing images to extract information about the Earth's surface. The spectral signature curve is a graphical representation of the reflectance of different materials at different wavelengths of the electromagnetic spectrum. This curve is useful for identifying different materials in remote sensing images. GPS, Global Positioning System, is a satellite-based navigation system that provides accurate location and time information. GPS is commonly used for field data collection and mapping applications in GIS. Aerial photography. Aerial photography involves taking photographs of the Earth's surface from an aircraft. Aerial photography is useful for mapping and monitoring land use and land cover, as well as for monitoring changes in vegetation and water resources. Satellite imagery. Satellite imagery involves taking images of the Earth's surface using remote sensing satellites. Satellite imagery is useful for mapping and monitoring land use and land cover, as well as for monitoring changes in vegetation and water resources. LiDAR, light detection and ranging, is an active remote sensing technique that uses laser pulses to measure the distance between the sensor and the Earth's surface. LiDAR is useful for measuring topography, vegetation structure, and soil moisture. Drones. Drones are unmanned aerial vehicles that can be used for remote sensing applications. Drones are useful for collecting high-resolution images and data in areas that are difficult to access using traditional aerial photography or satellite imagery. Overall, remote sensing technologies and techniques are essential tools for GIS analysis, allowing for the collection of data on the Earth's surface at a variety of scales and resolutions. Identification of required spatial data layers. Identifying the required spatial data layers is an important step in GIS analysis, as it ensures that the analysis is based on accurate and relevant data. Here are some general steps to follow when identifying the required spatial data layers for a GIS project. Define the problem or research question. The first step is to clearly define the problem or research question that the GIS analysis is intended to address. This will help to determine the types of data that are needed. Determine the scale and resolution. The scale and resolution of the GIS analysis will also help to determine the types of data that are needed. For example, if the analysis is focused on a small geographic area, high-resolution data may be required, whereas if the analysis is focused on a large geographic area, lower resolution data may be sufficient. Identify the data sources. Once the problem or research question has been defined and the scale and resolution of the analysis have been determined, the next step is to identify the data sources that are available. This may include publicly available data sources such as government agencies, or private data sources such as satellite imagery providers. Assess the quality of the data. It is important to assess the quality of the data before using it in a GIS analysis. This may involve checking for errors or inconsistencies in the data, or assessing the accuracy of the data using ground truthing techniques. Determine the required data layers. Based on the problem or research question, the scale and resolution of the analysis, and the availability and quality of the data sources, the required data layers can be identified. This may include layers such as land use, elevation, hydrology, transportation, or demographics. Overall, identifying the required spatial data layers is a critical step in GIS analysis, as it ensures that the analysis is based on accurate and relevant data that is appropriate for the problem or research question being addressed. Coding schemes in GIS. Coding schemes are used in GIS to represent attributes or characteristics of spatial data using numeric or alphanumeric codes. Coding schemes are used to standardize the representation of data, making it easier to store, process, and analyze. Here are some common coding schemes used in GIS. Numeric codes. Numeric codes are used to represent discrete values, such as land use categories or feature types. Numeric codes can be integers or floating point numbers, and they are often used in conjunction with lookup tables to translate the codes into meaningful values. Alphanumeric codes. Alphanumeric codes are used to represent values that contain both letters and numbers, such as postal codes or airport codes. Alphanumeric codes can be standardized using international or national standards, or they can be created for a specific project or dataset. Color codes. Color codes are used to represent values using a visual color scheme. Color codes are often used in thematic mapping, where different colors are used to represent different values or categories. Binary codes. Binary codes are used to represent values that have only two possible states, such as presence or absence, or yes or no. Binary codes are often used in spatial analysis to create binary rasters or to model binary relationships between features. Continuous codes. Continuous codes are used to represent values that can take on any value within a range, such as elevation or temperature. Continuous codes are often represented using color gradients or contour lines to visualize changes in values across space. Overall, coding schemes are an important tool in GIS for standardizing the representation of data and making it easier to store, process, and analyze. The choice of coding scheme depends on the type of data being represented and the specific requirements of the GIS project or analysis. National Urban Information System in GIS. National Urban Information System (NUIS) is a GIS-based system developed to support urban planning and management in India. It is a comprehensive system that integrates spatial and non-spatial data from various sources to create a database of urban areas in the country. The NUIS is aimed at providing reliable and accurate information on urban infrastructure, services, and resources to urban planners, administrators, and decision-makers at different levels. The NUIS database includes various layers of spatial and non-spatial data, such as land use, road network, drainage, water supply, sewerage, solid waste management, health facilities, education facilities, and other urban infrastructure and services. The data is collected from various sources, including satellite imagery, aerial photography, ground surveys, and administrative records. The MUIS is designed to support various urban planning and management activities, such as master planning, infrastructure development, disaster management, environmental planning, and monitoring and evaluation of urban programs and projects. The system allows users to visualize and analyze urban data using various GIS tools and techniques, such as spatial analysis, geocoding, and visualization. The MUIS is maintained and updated by the Ministry of Housing and Urban Affairs, Government of India. The system is available to various stakeholders, including urban planners, administrators, researchers, and the general public, through a web-based platform called the National Urban Information System (NUIS) web portal. The portal provides access to various data layers and tools for visualizing and analyzing urban data, as well as reports and publications on urban planning and management. Digitization of spatial data. Digitization is the process of converting analog spatial data, such as maps, photographs, or drawings, into digital form that can be used in a GIS. The process involves scanning or photographing the analog data, then using software to trace and digitize the features and attributes. The resulting digital data can then be used for spatial analysis, modeling, and visualization. Here are the steps involved in digitizing spatial data. Preparation. This involves preparing the analog data for digitization, such as cleaning the map or photograph and ensuring that it is in good condition for scanning or photographing. Scanning or photographing. The analog data is scanned or photographed using high-quality equipment to ensure that the resulting digital data is accurate and of high quality. Georeferencing. The digitized data is georeferenced, which means assigning spatial coordinates to the data so that it can be accurately placed in a GIS. Digitizing. The analog data is digitized using software that allows users to trace the features and attributes of the data. This can be done manually, using a mouse or digitizing tablet, or automatically, using image processing software. Editing. The digitized data is then edited to ensure accuracy and completeness, such as correcting errors or filling in missing information. Attribute data. Attribute data is added to the digitized data, such as land use categories or feature types. Quality control. The digitized data is then reviewed and checked for accuracy and completeness to ensure that it is suitable for use in a GIS. Overall, digitization is an important process in GIS, as it allows analog spatial data to be used in digital form, which can be analyzed and visualized using GIS tools and techniques. The process of digitization requires careful attention to detail and quality control to ensure that the resulting digital data is accurate and of high quality. Editing in GIS. Editing is a fundamental task in GIS that allows users to modify and update spatial and attribute data in a GIS database. The editing process can involve adding, deleting, or modifying features, as well as changing attribute values associated with features. Here are some key concepts related to editing in GIS. Edit mode. This is the mode in which the GIS software allows users to make changes to the database. In this mode, users can add, delete, or modify features and attribute data. Feature selection. Before making changes to a feature or set of features, users need to select them. This can be done by clicking on the features or by using a selection tool in the software. Attribute editing. Attribute editing involves changing the values associated with a feature. This can include modifying existing attributes or adding new ones. Spatial editing. Spatial editing involves modifying the geometry of a feature, such as moving, rotating, or resizing it. This can be done using a variety of editing tools, such as move, rotate, and scale tools. Snapping. Snapping is a feature that helps users align features with each other. For example, when digitizing new features, snapping can be used to ensure that they are accurately aligned with existing features. Undo/redo. These are important tools that allow users to undo or redo changes made during the editing process. This is useful when mistakes are made or when changes need to be reversed. Editing is a critical task in GIS, as it allows users to update and maintain spatial and attribute data in the database. The editing process requires careful attention to detail and accuracy to ensure that the resulting data is of high quality and suitable for use in GIS analysis and decision-making. Georeferencing of satellite imagery, cadastral map, role of attribute data in defining geographic features. Georeferencing is the process of assigning spatial coordinates to an image or map so that it can be accurately placed in a GIS or used for spatial analysis. Georeferencing is an important task in GIS, as it allows users to overlay different layers of data, such as satellite imagery and cadastral maps, and perform spatial analysis on the combined data. The process of georeferencing involves selecting a set of control points, which are known locations on the image or map that correspond to known locations in the real world. The control points are used to create a transformation that maps the image or map onto the correct location in the GIS. Once the georeferencing is complete, the image or map can be used for spatial analysis, such as overlaying it with other layers of data or extracting features from it. Attribute data is also an important aspect of GIS, as it provides additional information about the geographic features represented in the data. Attribute data can include information such as the name, size, and type of features, as well as other descriptive information. Attribute data is used to define and classify geographic features in a GIS, and can be used to filter and query the data based on specific attributes. For example, cadastral maps may include attribute data such as property ownership, zoning information, and building heights. This information can be used to perform spatial analysis, such as identifying areas that are zoned for residential use and have building heights that exceed a certain threshold. Satellite imagery may include attribute data such as vegetation type, land cover, and surface temperature, which can be used to analyze changes in land use over time or to model the effects of climate change on the environment. In summary, georeferencing and attribute data are critical components of GIS, as they allow users to accurately place geographic features in a GIS and to provide additional information about the features that can be used for spatial analysis and decision-making. Adding attribute data file. Adding attribute data to a GIS is a common task that involves importing data from external sources, such as spreadsheets or databases, and associating the data with the corresponding geographic features in the GIS. Here are the basic steps for adding attribute data to a GIS. Prepare the attribute data. The first step is to prepare the attribute data that you want to add to the GIS. This typically involves organizing the data into a spreadsheet or database format and ensuring that the data is formatted correctly and has the necessary fields. Import the attribute data. Once the attribute data is prepared, you can import it into the GIS. Most GIS software has tools for importing data from a variety of sources, including spreadsheets, databases, and text files. The data can be imported into a new table in the GIS or added to an existing table. Link the attribute data to geographic features. After importing the attribute data, you need to link it to the corresponding geographic features in the GIS. This is typically done by creating a common field in both the attribute data and the GIS feature layer, and then joining the two tables based on this common field. Once the tables are joined, the attribute data can be associated with the corresponding geographic features in the GIS. Edit the attribute data. Once the attribute data is linked to the GIS feature layer, you can edit the data as needed. This might include adding or deleting records, updating attribute values, or filtering the data based on specific criteria. Adding attribute data to a GIS is an important task, as it allows users to associate additional information with the geographic features in the GIS. This information can be used to perform spatial analysis and to create maps and visualizations that help support decision-making. Topology generation. Topology generation in GIS refers to the process of creating and maintaining topological relationships between geographic features in a GIS. Topology is the spatial relationship between geographic features, such as adjacency, connectivity, and containment. Topology is important in GIS because it ensures that spatial analysis and editing operations are performed correctly and that data is consistent and accurate. There are several steps involved in topology generation in GIS. Create feature classes. The first step is to create feature classes for each type of geographic feature that will be included in the topology. For example, a feature class might be created for roads, another for buildings, and another for water bodies. Define rules. Next, rules are defined that specify how the different feature classes should relate to each other in terms of topology. For example, a rule might specify that roads cannot intersect buildings, or that water bodies must be contained within a specific boundary. Build topology. Once the rules are defined, the topology can be built by running a topology generation tool in the GIS software. This tool creates and maintains the topological relationships between the geographic features based on the specified rules. Edit topology. After the topology is built, it can be edited as needed to correct errors or make changes to the topological relationships between features. Validate topology. Finally, the topology can be validated to ensure that it is accurate and consistent. This involves running checks to identify topological errors, such as gaps, overlaps, or dangling features. Topology generation is an important aspect of GIS, as it helps ensure that the data is consistent and accurate, and that spatial analysis and editing operations are performed correctly. Topology can also help identify errors or inconsistencies in the data, which can be corrected to improve the overall quality of the GIS data. Joining attribute data to its geographic features. Joining attribute data to its geographic features is a common task in GIS, and it involves linking data from an external source to its corresponding geographic feature in the GIS. This process is also known as a table join or data join. Here are the basic steps for joining attribute data to its geographic features. Identify the common field. The first step is to identify a common field that exists in both the attribute data and the geographic feature layer. This field serves as the linking mechanism between the two datasets. Prepare the attribute data. The attribute data must be prepared to match the format of the common field in the geographic feature layer. This includes ensuring that the field name matches exactly, and that the data types and values are compatible. Open the Join Data tool. In most GIS software, the Join Data tool can be found in the Data Management or Table Tools menu. Open this tool to start the joining process. Specify the datasets. In the Join Data tool, specify the geographic feature layer and the attribute data that you want to join together. Make sure to select the common field as the linking mechanism. Choose the join type. Choose the type of join that you want to perform. The most common types are inner join, left join, and right join. Each join type has different implications for the resulting dataset, so choose the appropriate type based on your needs. Validate the join. After the join is performed, it is important to validate the results to ensure that the data is correctly linked. This can be done by examining the resulting table or running validation tools in the GIS software. Joining attribute data to its geographic features is an important aspect of GIS analysis, as it allows users to incorporate additional information into their maps and analyses. By linking external data to geographic features, users can perform spatial analysis and create visualizations that help support decision-making. Unit 3. Spatial analysis using GIS. Spatial analysis is a process of examining spatial patterns and relationships among geographic features using GIS software. It involves the application of various analytical techniques to understand and interpret spatial data. Here are some of the commonly used spatial analysis techniques in GIS. Overlay analysis. This technique involves combining multiple spatial datasets to create a new output layer. The overlay can be used to identify areas of overlap, proximity, or conflict between different features. Buffer analysis. Buffer analysis is a spatial analysis technique that involves creating a buffer zone around a specific feature or set of features. The buffer zone can be used to analyze proximity or accessibility to certain features or resources. Spatial interpolation. Spatial interpolation is the process of estimating unknown values at specific locations based on known values from surrounding locations. This technique is commonly used for creating surface maps or identifying spatial patterns in data. Network analysis. Network analysis is a spatial analysis technique that involves analyzing the connectivity and accessibility of different features in a network, such as roads, waterways, or communication networks. Spatial statistics. Spatial statistics involves the application of statistical techniques to spatial data. This includes techniques such as spatial regression, cluster analysis, and hotspot analysis. Geostatistics. Geostatistics is a branch of spatial analysis that focuses on the analysis of spatially correlated data. This includes techniques such as kriging, which is used for predicting values at unsampled locations based on the spatial correlation of nearby values. Spatial analysis using GIS can be applied in various fields such as urban planning, environmental management, public health, and natural resource management. It helps in identifying spatial patterns and relationships among geographic features, which can aid in making informed decisions and policy recommendations. Generation of 3D model in GIS. GIS software can be used to generate 3D models of geographic features and landscapes. Here are the basic steps involved in generating a 3D model in GIS. Data collection. The first step in generating a 3D model is to collect data, including elevation data and feature data, such as building footprints and land cover. Data preparation. Once the data is collected, it needs to be prepared for use in the 3D model. This may include cleaning and processing the data to remove any errors or inconsistencies. Data integration. The elevation data and feature data need to be integrated in order to create a complete 3D model. This involves combining the data and assigning elevation values to each feature. Visualization. The 3D model can then be visualized in GIS software, allowing users to explore and analyze the data in a three-dimensional space. Analysis. The 3D model can be used to perform various spatial analyses, such as line-of-sight analysis, terrain analysis, and volumetric analysis. GIS software offers a variety of tools and techniques for creating and analyzing 3D models, including digital elevation models, DEMs, 3D surface modeling, and 3D point clouds. The resulting 3D models can be used in a range of applications, from urban planning and architecture to environmental management and natural resource exploration. Performing overlay functions. Overlay analysis is a powerful spatial analysis technique used in GIS to combine multiple spatial datasets into a single layer. Overlay functions can be performed using GIS software and involve a process of combining two or more spatial data layers to create a new output layer. Here are the basic steps involved in performing an overlay function. Select the input layers. The first step in performing an overlay function is to select the input layers that will be used in the analysis. These can include vector layers such as points, lines, and polygons, as well as raster layers such as elevation data or satellite imagery. Define the overlay function. Once the input layers are selected, the next step is to define the overlay function that will be used to combine them. Common overlay functions include intersect, union, and difference. Specify the output layer. After defining the overlay function, the user needs to specify the output layer where the results of the overlay analysis will be stored. Adjust the attributes. Depending on the overlay function used, the user may need to adjust the attributes of the resulting layer. For example, if two layers are intersected, the resulting layer may contain only the attributes of the input layer with the fewest attributes. Perform the overlay function. Once all the parameters are set, the overlay function can be performed, and the resulting layer can be visualized and analyzed in GIS software. Overlay functions are commonly used in various fields such as urban planning, environmental management, and natural resource exploration. They can be used to identify areas of overlap or conflict between different spatial datasets, and to create new spatial data layers that integrate multiple sources of information. Manipulating attribute data. Attribute data manipulation is an important part of GIS analysis, as it allows users to extract, analyze, and visualize specific data attributes within a spatial dataset. Here are some common techniques for manipulating attribute data in GIS. Querying. Querying is a process of selecting specific features from a dataset based on their attributes. Users can use SQL-like expressions to select features based on specific attribute values or combinations of values. Joining. Joining is a process of combining attribute data from one dataset with attribute data from another dataset based on a common field. This allows users to add additional information to a dataset, such as demographic or environmental data. Calculating. Calculating is a process of creating new attributes in a dataset based on mathematical or logical expressions. This can include calculations of distance, area, and volume, or more complex calculations based on multiple attributes. Classifying. Classifying is a process of grouping features in a dataset based on their attribute values. This allows users to create thematic maps that highlight specific features or patterns in the data. Symbolizing. Symbolizing is a process of assigning visual symbols to features based on their attribute values. This allows users to create maps that effectively communicate the data to others. Attribute data manipulation is an essential part of GIS analysis and enables users to extract meaningful information from spatial data layers. By manipulating attribute data, users can gain insights into the relationships between different features and make informed decisions about a range of spatial problems. Preparation of existing land use. Preparing an existing land use map is an important part of land use planning and management. Here are some basic steps involved in preparing an existing land use map. Define the study area. The first step in preparing an existing land use map is to define the study area. This can be done using administrative boundaries, topographic features, or other geographic features. Acquire base data. Once the study area is defined, the next step is to acquire base data such as satellite imagery, aerial photography, or topographic maps. This base data is used to identify and map the different land use features in the study area. Classify land use features. Using the base data, the land use features in the study area can be classified into different categories such as residential, commercial, industrial, agricultural, and open space. This classification can be done manually or using automated image processing techniques. Digitize land use features. Once the land use features are classified, they can be digitized using GIS software. This involves tracing the boundaries of each feature using a digitizing tablet or mouse. Assign attributes. Once the land use features are digitized, attributes such as land use type, area, and ownership can be assigned to each feature. This information is used to analyze and visualize the data in GIS software. Validate and refine the data. Finally, the land use map should be validated and refined by comparing it to other available data sources or field observations. This helps to ensure that the land use map accurately reflects the actual land use features in the study area. Preparing an existing land use map is an important part of land use planning and management. It provides valuable information on the spatial distribution of land use features and can be used to identify trends and patterns in land use change over time. The land use map can also be used as a baseline for future land use planning and management activities. Map and report generation. Once the spatial and attribute data has been collected, processed, and analyzed using GIS software, it can be used to generate maps and reports. Here are some basic steps involved in map and report generation in GIS. Define the purpose and audience. The first step in map and report generation is to define the purpose and audience for the map or report. This helps to determine what information should be included, what format should be used, and how the information should be presented. Select appropriate data layers. Once the purpose and audience are defined, the appropriate data layers can be selected. This may include base maps, thematic maps, and other relevant data layers such as roads, land use, or population density. Design the layout. The next step is to design the layout of the map or report. This involves selecting the appropriate scale, orientation, and projection for the map, as well as deciding on the placement of the legend, title, and other elements. Customize symbology. Once the layout is designed, the symbology for each data layer can be customized to highlight important features or trends. This may include changing the color, size, or style of the symbols used to represent different data categories. Generate the map or report. Once the layout and symbology are finalized, the map or report can be generated using GIS software. This may involve exporting the map as a digital image or generating a printable report in PDF format. Validate and refine the output. Finally, the map or report should be validated and refined by reviewing it for accuracy and completeness. Any errors or omissions should be corrected before the final version is shared with the intended audience. Generating maps and reports is an important part of GIS analysis and communication. It allows stakeholders to visualize and understand complex spatial and attribute data, and can be used to support decision-making and planning activities. Network analysis. Network analysis is a GIS tool that is used to model, analyze, and solve problems related to transportation, distribution, and other network systems. It involves creating a network dataset from existing spatial data, such as road or rail networks, and then using that dataset to perform a variety of analyses. Here are some common network analysis techniques used in GIS. Route analysis. Route analysis involves finding the shortest or fastest path between two or more points on a network. This can be used for finding optimal travel routes, delivery routes, or emergency response routes. Service area analysis. Service area analysis involves determining the area that can be reached within a given time or distance from a particular location on the network. This can be used for determining catchment areas for businesses, emergency services, or public transportation. Location allocation analysis. Location allocation analysis involves finding the optimal location for one or more facilities on a network, taking into account factors such as demand, cost, and accessibility. This can be used for siting new businesses or services, or for optimizing distribution networks. Network tracing. Network tracing involves following the path of network features, such as water or gas pipelines, to identify issues such as leaks or breaks. This can be used for maintenance and repair activities. Network analysis is a powerful tool for solving problems related to transportation, distribution, and other network systems. It allows users to model and analyze complex systems, and can be used to support decision-making and planning activities. Unit 4. Modeling the macro environment. Modeling the macro environment using GIS involves analyzing and understanding the complex relationships between various environmental factors and their impact on human activities. Some of the factors that can be modeled using GIS include land use, topography, vegetation, water resources, climate, and natural hazards. Here are some examples of how GIS can be used to model the macro environment. Land use planning. GIS can be used to analyze land use patterns and identify areas suitable for different types of development. For example, GIS can be used to identify areas for residential, commercial, or industrial development, and to determine the appropriate zoning regulations for each area. Natural hazard mapping. GIS can be used to map areas prone to natural hazards such as floods, landslides, or earthquakes. This information can be used to inform land use decisions and to develop emergency response plans. Climate change modeling. GIS can be used to model the impact of climate change on various environmental factors such as vegetation, water resources, and land use patterns. This information can be used to develop adaptation strategies and to inform policy decisions. Ecosystem management. GIS can be used to model ecosystems and their interactions with human activities. For example, GIS can be used to identify areas of high biodiversity, to model the impact of land use changes on ecosystem services such as water purification and carbon sequestration, and to develop conservation strategies. In summary, GIS can be used to model the macro environment by analyzing and visualizing complex relationships between various environmental factors. This information can be used to support decision-making and planning activities related to land use, natural hazards, climate change, and ecosystem management. Need for modeling the macro environment for different scales and purposes. Modeling the macro environment is important for different scales and purposes because it helps to provide a better understanding of the complex relationships between environmental factors and human activities. Here are some of the reasons why modeling the macro environment is needed. Planning and decision-making. Modeling the macro environment is essential for planning and decision-making related to land use, natural resource management, disaster risk reduction, and climate change adaptation. By understanding the spatial relationships between environmental factors and their impact on human activities, decision-makers can develop more effective and sustainable strategies. Resource management. Modeling the macro environment can help to identify areas of high biodiversity, water resources, and other natural resources, and to develop sustainable management strategies that balance human needs with environmental conservation. Disaster risk reduction. Modeling the macro environment is important for identifying areas that are prone to natural hazards such as floods, landslides, and earthquakes. By understanding the spatial relationships between these hazards and human settlements, decision-makers can develop effective disaster risk reduction strategies. Climate change adaptation. Modeling the macro environment is important for understanding the impact of climate change on different environmental factors and their impact on human activities. This information can be used to develop adaptation strategies that reduce vulnerability and increase resilience. Sustainable development. Modeling the macro environment is essential for promoting sustainable development that balances human needs with environmental conservation. By understanding the complex relationships between environmental factors and human activities, decision-makers can develop more sustainable land use and resource management strategies. In summary, modeling the macro environment is needed for different scales and purposes to provide a better understanding of the complex relationships between environmental factors and human activities, and to support planning and decision-making related to resource management, disaster risk reduction, climate change adaptation, and sustainable development. Modeling for suitability/projects/situations/problems in the realm of landscape design, urban and environmental planning. Modeling is an essential tool for landscape design, urban design, and environmental planning. Here are some examples of how modeling can be used in these fields. Suitability analysis. Modeling can be used to identify the most suitable locations for different land uses and activities. For example, suitability models can be used to identify areas that are most suitable for parks, commercial development, or residential areas. These models take into account various factors such as topography, soil characteristics, proximity to amenities, and other relevant factors. Project planning. Modeling can be used to support the planning and design of infrastructure projects such as highways, water supply systems, and waste management systems. By using models that take into account factors such as traffic patterns, population density, and environmental impact, designers can develop more effective and sustainable solutions. Environmental planning. Modeling can be used to assess the potential impact of development on the environment. Environmental impact assessment models can be used to identify areas of high ecological sensitivity and to develop strategies that minimize the impact of development on these areas. Urban design. Modeling can be used to support the design of urban spaces such as streets, parks, and plazas. By using models that take into account factors such as pedestrian flow, shading, and microclimate, designers can develop more functional and comfortable spaces. Landscape design. Modeling can be used to support the design of outdoor spaces such as gardens, parks, and public spaces. By using models that take into account factors such as terrain, vegetation, and microclimate, designers can develop more effective and sustainable designs. In summary, modeling can be used in landscape design, urban design, and environmental planning to support suitability analysis, project planning, environmental planning, urban design, and landscape design. By using models that take into account relevant factors, designers and planners can develop more effective and sustainable solutions that promote the well-being of people and the environment. Course outcomes. Various awareness of GIS and the context of its use for different purposes. GIS, Geographic Information System, is a versatile tool that can be used in various fields and for different purposes. Here are some examples of how GIS can be used in different contexts. Urban and regional planning. GIS can be used in urban and regional planning to analyze data related to land use, population, transportation, and infrastructure. GIS can help planners identify areas of high growth, assess the impact of development on the environment, and develop strategies to manage growth and change. Environmental management. GIS can be used in environmental management to analyze data related to natural resources, pollution, and climate change. GIS can help managers identify areas of high risk, assess the impact of human activities on the environment, and develop strategies to mitigate these impacts. Public health. GIS can be used in public health to analyze data related to disease outbreaks, vaccination rates, and health services. GIS can help health officials identify areas of high risk, assess the distribution of health services, and develop strategies to improve access to care. Transportation. GIS can be used in transportation planning to analyze data related to traffic flow, congestion, and safety. GIS can help transportation planners identify areas of high congestion, assess the safety of roads and highways, and develop strategies to improve traffic flow. Natural resource management. GIS can be used in natural resource management to analyze data related to forestry, agriculture, and wildlife. GIS can help managers identify areas of high biodiversity, assess the impact of human activities on natural resources, and develop strategies to conserve these resources. In summary, GIS is a powerful tool that can be used in various fields and for different purposes. By analyzing data related to geography and spatial relationships, GIS can help decision-makers make more informed decisions that promote sustainability, efficiency, and well-being. Knowledge of concepts, techniques, methods of GIS. To effectively use GIS, it is important to have knowledge of the concepts, techniques, and methods that are used in GIS. Here are some key concepts and techniques used in GIS. Spatial data. Spatial data refers to data that is related to geographic locations. This can include data such as coordinates, boundaries, and addresses. Attribute data. Attribute data refers to non-spatial data that is associated with spatial data. This can include data such as population, land use, and ownership. Geocoding. Geocoding is the process of assigning a geographic location to an address or other non-spatial data. Projection. A projection is a method of representing the Earth's curved surface on a flat surface, such as a map, to identify issues such as leaks or breaks. This can be used for maintenance and repair activities. Coordinate systems. Coordinate systems are used to assign unique coordinates to locations on the Earth's surface. Remote sensing. Remote sensing involves the use of satellite or aerial imagery to gather information about the Earth's surface. Spatial analysis. Spatial analysis involves using GIS to analyze spatial data, such as overlaying different layers of data to identify relationships and patterns. Cartography. Cartography is the process of creating maps using GIS. Database management. GIS involves managing large amounts of data, including spatial and attribute data. Database management skills are important for effectively using GIS. Programming. Programming skills can be useful in GIS for automating processes and customizing GIS applications. By having a solid understanding of these concepts and techniques, GIS professionals can effectively use GIS to solve complex spatial problems and make informed decisions based on spatial data. Ability to apply GIS for specific situations/realms involving the built environment. The ability to apply GIS for specific situations and realms involving the built environment requires a deep understanding of the built environment and how it interacts with spatial data. Some examples of how GIS can be applied in the built environment include urban planning. GIS can be used in urban planning to analyze and visualize data related to population demographics, land use patterns, transportation networks, and environmental factors. This can help planners make informed decisions about how to allocate resources and plan for future growth. Architecture. GIS can be used in architecture to analyze and visualize data related to building sites, building codes, and environmental factors. This can help architects make informed decisions about building design and site selection. Real estate. GIS can be used in real estate to analyze and visualize data related to property values, zoning regulations, and market trends. This can help real estate professionals make informed decisions about buying and selling properties. Environmental management. GIS can be used in environmental management to analyze and visualize data related to natural resources, such as water quality, air quality, and soil erosion. This can help environmental professionals make informed decisions about how to manage and protect these resources. Disaster management. GIS can be used in disaster management to analyze and visualize data related to natural disasters, such as hurricanes, earthquakes, and wildfires. This can help emergency responders make informed decisions about how to allocate resources and respond to these disasters. Overall, the ability to apply GIS for specific situations and realms involving the built environment requires a strong understanding of both GIS concepts and the built environment. By effectively using GIS, professionals can make informed decisions and solve complex problems in the built environment. Various ability to apply GIS for specific situations/realms involving the built environment. The ability to apply GIS for specific situations and realms involving the built environment requires a deep understanding of the built environment and how it interacts with spatial data. Some examples of how GIS can be applied in the built environment include urban planning. GIS can be used in urban planning to analyze and visualize data related to population demographics, land use patterns, transportation networks, and environmental factors. This can help planners make informed decisions about how to allocate resources and plan for future growth. Architecture. GIS can be used in architecture to analyze and visualize data related to building sites, building codes, and environmental factors. This can help architects make informed decisions about building design and site selection. Real estate. GIS can be used in real estate to analyze and visualize data related to property values, zoning regulations, and market trends. This can help real estate professionals make informed decisions about buying and selling properties. Environmental management. GIS can be used in environmental management to analyze and visualize data related to natural resources, such as water quality, air quality, and soil erosion. This can help environmental professionals make informed decisions about how to manage and protect these resources. Disaster management. GIS can be used in disaster management to analyze and visualize data related to natural disasters, such as hurricanes, earthquakes, and wildfires. This can help emergency responders make informed decisions about how to allocate resources and respond to these disasters. Transportation planning. GIS can be used in transportation planning to analyze and visualize data related to traffic patterns, transportation infrastructure, and accessibility. This can help transportation planners make informed decisions about how to improve transportation systems and alleviate traffic congestion. Historic preservation. GIS can be used in historic preservation to analyze and visualize data related to historic sites and buildings, as well as environmental factors that can impact these sites. This can help historic preservationists make informed decisions about how to preserve and protect these important cultural resources. Overall, the ability to apply GIS for specific situations and realms involving the built environment requires a strong understanding of both GIS concepts and the built environment. By effectively using GIS, professionals can make informed decisions and solve complex problems in the built environment.